This will be posted upstairs real quick. Resonance structures, put anion on carbon and then on oxygen, 6 high electrons there. Far right, most electron rich. All the others, the lone pair is conjugated with the ring. The one on the right, the lone pair is not conjugated, so it's not delocalized. Product on the far right, Diels-Alder, trans, bridge, 1 carbon bridge. And the acylium ion, triple bond, charge on oxygen. This will be posted upstairs, guys. Lab reports, group lab reports. Please pass them to the center. Any other group lab reports? Pass them up, please. Any other group lab reports? I'll pass back the Friday lab TLC sheets at the end of class. We need to pick up with substitution.
We're off next week.
Okay, guys. Substitution has many components. In general, we have nucleophile component and electrophile component. The electrophile contains the leaving group. We looked at that reactant or species. Right now we're looking at the nucleophile. Up top, sterics. Sterics greatly influences nucleophilic strength. The ones on the far right, much more steric and hindered than the ones on the left. I believe we ended about right there. Tert-butoxide, that's called, often used as a non-nucleophilic base for two eliminations. Once we start elimination, we'll start talking about that. That's on the yellow handout. Okay. We mentioned this here. Next, resonance effects. Let's look at these two potential nucleophiles. They're both anions. They're both oxygen, both anions. So what's the difference? Of course, they have lone pairs, right? This is a much better nucleophile. This oxygen anion is actually resonance delocalized. Right? We can do electrons in, electrons up, and we get resonance structure. The true structure of a hybrid, right? Boom, boom, boom. The true structure has partial minus if you blend these two together. We've done that before. So this is really the true structure. So full minus on oxygen or partial minus on oxygen, which is going to be more nucleophilic, that is more attracted to a positive. Full minus. This is not really a full minus. So you got to know that the resonance is here and that this is not really a true structure. It's a fake structure. The hybrid is really your true structure. The charge is spread out, making it less nucleophilic, less electron-rich, etc. This is a stronger nucleophile. It's not delocalized. Same thing over here. Which lone pair is delocalized? Left or right? Here, delocalized. We can draw resonance structure into the ring, and we can put anion. We can put lone pair on carbon, and it thus be an anion. There's another way to look at this as well. We could look at over here. What type of orbital is this lone pair in? This lone pair is in sp3. This lone pair is in what type of orbital? P orbital. Lone pairs in p orbitals are not going to be basic or nucleophilic. Or I should say that basic or that nucleophilic. It's going to be much less basic or nucleophilic than the sp3 lone pair. This lone pair is busy doing resonance. It's delocalized by resonance. So, these are resonance effects. Resonance is typically going to decrease your nucleophilic strength of your atom you're looking at. Next, hybridization effects. Now again, a lot of this mirrors our acid-base discussion from 2 months ago. Pull out that handout. Nucleophile and base, very similar. Some differences. The main differences comes again with sterics. Sterics greatly influences or decreases nucleophilic strength, but it doesn't affect basic strength. Again, because the proton is so small, it's a spherical s orbital. Sterics doesn't matter at acid base. So up top again, this guy is a poor nucleophile, or relatively poor, more poor than those, because it's got this sterics, these wings. But it's still a good base, because sterics doesn't matter for base. Okay? Poor nucleophile, but still used as a base, good base. Okay, hybridization effects. Again, I'd recommend pulling out your acid-base handout. We kind of did hybridization up there a little bit when we asked about the lone pair. This lone pair is in what type of orbital? sp3. This lone pair is in sp2 or p? Who says p?
No, it says sp2. I'm sorry.
Who says sp2? Yes, sp2. Not in a p orbital. If you graph it, you'll see it's not in a p orbital. We spent some substantial time on that, week 2, week 3. Okay? Which lone pair is held tighter to the nucleus? This one, more S character, held tighter to the nucleus. Thus, it's going to be less likely to go do a backside attack. More nucleophilic. Also more basic. Okay, again, nucleophile base mirrors, except for sterics. Summing it up, rank. How do we do on these? Rank each of the following according to nucleophilic strength, from weakest to strongest. I should probably change that. It'd probably be easier to start with strongest. To me, I'd probably prefer to start with strongest. We can turn the ranking around. What's the strongest nucleophile in #1 series?
Sodium
Okay, this is organic chemistry. Regardless of that, we know that sodium is a spectator ion, right? This is S minus, this is O minus, this is O minus, and that's neutral oxygen. All right, maybe it is the, maybe weakest would be easier. What's the weakest nucleophile? Why water? Because it's neutral. Water's weakest. Okay, we're going from weakest to strongest. So we rank that as 1. See, that's what I don't like. 1 sounds like it's the best. Here, 1's the weakest. Okay. What's next? Well, do we even know what AC stands for? That's acetate. You should know structure of acetate, right? You should have learned acetate in Gen Chem. It's a polyatomic ion. That's what they call it in Gen Chem. Right? These two are very darn similar. Can we distinguish between these? O minus or S minus? Stronger is why S minus? Bigger? What's another reason though?
The electrons aren't as close, or is it held as tightly?
Electrons aren't held as tightly. Oxygen's a better parent. More electronegative, holds the electrons tight. Even though it's a minus, it still holds it tight. Not as good a parent. Bigger, the electrons are out there. Yes, this is stronger. That's stronger than that. Okay, I don't know what we put here. 1, 2, 3. Let's just keep that in mind. How about these two here? They're both oxygens. Huh? We've already done this today, right? Which one's stronger? This is resonance delocalized anion. This is just a pure anion. There's no resonance here. Which one's stronger? That's stronger. Okay, see, this is where I've heard. I like stronger in my mind. The strongest up here is which one? Right here. Let's call it 4. What's next? OH or OACL? Yeah. 4, 3, 2, 1. There you go. There's your ranking. With 1 being the weakest, 4 being strongest. Questions about that ranking? About the one below? All these are anions, right?
Does that TBU stand for tert butyl?
Yes, tert butyl. T-butyl, tert butyl. Tertiary butyl. 4 carbons. The oxygen's coming off the tertiary side is anion. Okay, very common. Thanks for asking. A very common abbreviation. OT-butyl is here. Versus O-methyl. Okay, just CH3, O-methyl. Which one's strongest up here? O minus or N minus? Which one's more electronegative? O holds it tighter. Nitrogen is not as good of a parent. It lets its electrons get out there and do backside attack. That's stronger than these two. Do you think that's stronger than these? These are halides, very electronegative. They really hold the lone pair. I think this is the strongest, and since we're ranking it, that should be 1, 2, 3. That should be 5. What's the weakest? The weakest is going to be these that hold the electrons real tight. Which is weaker, F minus or Cl minus? Okay, again, we're talking about nucleophile.
So this is electronegative?
So this is where there's another, it's conflicting other than sterics. Which is a weaker nucleophile, F minus or Cl minus?
F minus.
I didn't hear anybody.
F minus.
F minus is a weaker nucleophile?
Because it's got atomic radius that's smaller than 4.
It holds one tighter than Cl. There's electron.
I agree. The weakest up here is F minus. What's next?
Chloride.
Cl minus. Cl minus is a stronger nucleophile, but it's a weaker base. And this ain't steric. So here's another thing where there's conflicting between nucleophile. Whenever we were doing, what's a stronger base, F minus or Cl minus? F minus. And the reason is, we said because F minus was less stable. It's less stable, so it wants to go back to neutral. It wants to take an H and go back to neutral. Also, I mean, just which is a stronger acid, HF or ACl? It's a stronger acid. Why? Because Cl minus is more stable than F minus. That's why we said this is more stable. Thus, this guy wants to go back more, so it's a stronger base. Because it's less stable. But it's a weaker nucleophile. See, that's where it's really conflicting. With nucleophiles, the less electronegative is a worse pairing. That really takes some looking at. This is much more. Understanding sterics is pretty straightforward. Why sterics make something a worse nucleophile. This is more. You got to really look at this and understand that. Okay, that's 1 and 2 for the worse. Okay, how about these two? Which is worse? What's the worst nucleophile here? Yes, tert-butyl. Why? Sterics. Sterics makes this worse than that. Otherwise, they're the same. O minus. So 1, 2, 3, 4, 5. Worst. Strongest nucleophile. Stronger nucleophile than this. Better nucleophile. It doesn't have any sterics. Okay. So you can think about those rankings. Let's look at the next. What's it say at the bottom? You summing it up. What type of nucleophile can participate in an SN2 reaction? Maybe I should put this up here. Only strong ones for SN2. We've got to keep in mind, the nucleophile is involved in the rate determining step of an SN2. Since it's involved in the rate determining step, it needs to be strong. Turns out. It needs to be strong. Is nucleophile involved in the rate determining step of SN1? No. SN1, the new rate determining step is leaving group leaving. The nucleophile has nothing to do with that. Okay? Needs to be strong. Well, which ones are strong? Because in the previous page, we didn't call them strong or weak. We only called them stronger. We were relative. Which ones are strong? Just like we said with bases. Anions or sp3 amines. Those are your strong nucleophiles. Now, so any anion is strong according to this. The problem is not every single anion is strong. Okay? Some halides are not strong, some highly conjugated anions are not strong. But for an opening statement, anions and sp3 amines. So, here we go. Which compounds are strong nucleophiles? Is this a strong nucleophile? Got a long pair. Strong or weak? Is it an anion? Is it an sp3 nitrogen? Then it's weak. Next. Is it an anion? Is it an sp3 nitrogen? Then it's weak. Next. Is it an anion?
Yes.
Yes. Strong. Is it an anion? No. Is it an sp3 nitrogen?
Yes.
Yes. Strong. Anion? No. sp3 nitrogen? No. That nitrogen's sp2. But even, we got to get even more specific than that because a lone pair is in what type of orbital? Lone pairs in p orbital is not basic. Here's another little exception up here. We can sort of sp2 lone pair is somewhat basic. sp3 definitely basic. sp2 is borderline. But once you start talking about sp2, you got to clarify: is the lone pair in an sp2 or p? Because you have two possibilities. If it's in a p, it's certainly not basic, or drastic, or much less basic. Some sp2, for example, on the previous page we had that. Is this a strong nucleophile? Yes, lone pairs in sp3. What about this guy? Strong? This is a borderline strong, because the lone pairs in what type of orbital? It's already on your page.
SP2.
sp2, borderline strong. Okay? Usually I'll say anions sp3, sp2 kind of as well. KCN. Well, that's cyanide, right? Weak or strong? Strong. H2O. Weak. So, are you going to do an SN2 reaction with water? No. Only the ones we circled. Now, any statement has some exceptions. Could you see an SN2 reaction with water? And first off, I'd be very hesitant to believe it. But then maybe there's some other data or something to consider. Okay? Or maybe it's done at 1,000 degrees, and maybe it works then. But that's very difficult to do, a reaction at 1,000 degrees. So again, very often these opening statements have some exceptions. For us, sometimes maybe we'll be given other things to consider, etc. Okay, at this point, let's look at various SN2 examples. Thus far, it's been sort of very general. First, alkylation of oxygen. Let's look right here. Is this a strong nucleophile for SN2? No, weak, neutral. It's a carboxylic acid, though. What if it was in the form of the anion? Is that strong? Yes. This guy will do an SN2. Okay? We're going to call a strong nuke. Now again, that doesn't mean it's the strongest you'll ever see. There's many other stronger ones, but we're calling this strong. If we bring in some carbon to the leaving group, by the way, what type of carbon must the leaving group be on? We should have discussed this last time, but we didn't appear to be prepared to discuss it. What type of carbon does the leaving group need to be on? Tetrahedral? Right. Everybody got that last time? If you didn't pick that up, I'd refer back to the title of the handout. Right there it is. All right. So a leaving group on a tetrahedral carbon. Then we can come in and we can do a backside attack, concerted backside attack. Good old SN2, right? And make bond to carbon. We just made that bond. And what did we put on the oxygen? alkyl group. So we did an alkylation of a carboxylic acid. Okay, here's the acid. It's now been alkylated. But first we had to turn it into a good nucleophile. Bad nucleophile. How do we get here? We just need to remove an H+. What would you do this? What reagent would you use? How about sodium hydroxide? Would hydroxide remove this proton to an acid-base reaction? Yeah. Make that plus water, right? So, to do an SN2, we must first make the oxygen anion. Carboxylic acids, you can use sodium hydroxide or potassium hydroxide. You can use a variety of bases. What about regular alcohols? They're just alcohols. Can you make the anion using sodium hydroxide? But we need to use our pKa's. Obviously not, big X. pK of an alcohol is 16. Okay? Through this reaction, we're going to make water. What's its pKa? 16. Which side's favored? Neither side's favored. Now, actually, at equilibrium, you got half of this made. Problem is, for acid-base reactions to work in any practical manner, that is, in the lab, you need to have a pKa difference of about 2 to 3. Okay? 16 ain't going to work in lab. All right, we could spend a couple of lectures talking about the equilibrium, why it just practically doesn't work. Even bringing in Le Chatelier's principle, it still ain't going to work. In the end, hydroxide is not strong enough to deprotonate an alcohol at 16, but it is strong enough to deprotonate a carboxylic acid because its pKa is about what?
4 to 5.
About 4 to 5. Much more acidic. That works. This does not. You guys also, I know many of you don't see the anion here because on quizzes, tests, everything, it's like you don't realize that this is an anion. Get rid of that. This is O-, just like that there. Sometimes spectator ions may be shown, sometimes not. So if we can't use sodium hydroxide, what can we use? We can use sodium metal. Okay? That's not a plus or anything, it's sodium 0, sodium metal. Right? Sodium metal with an alcohol, we can get the anion. By the way, what do you want to call the anion? This is an alcohol. What do you want to call the anion? What do you call this anion? Hydroxide. Like it's hydrogen oxide, hydroxide. Okay. What if we put an alkyl group on the oxygen? It's an alkyl group oxide. Alkoxide. Okay. It's called an alkoxide. This would be the sodium alkoxide. We can make alkoxides from the alcohols using sodium. It generates hydrogen gas. That's the fate of the H. Now, if you want to balance this, go for it. You got 2 H's over there, so you're going to need 2 of these. Okay? So it's not balanced. Now, this is a redox reaction. That is, we're not going to show any acid-base. This has no lone pair. It's not going to take the proton. It's pure redox. It's radical reaction. Not going to show a mechanism. Sodium is 0 here. What's the oxidation state of the sodium here? +1. So the sodium's been oxidized. What's been reduced? You've probably never seen oxidation states given of organic like this, but here the H is +1. It's considered like if it's H+ proton. What's the oxidation state of the H here? It's an element here, hydrogen elemental hydrogen, what's its oxidation state?
0, 0.
0. So the H has been reduced. Okay, there's redox here. You can see it easier from the sodium. There's a good old classical reaction. If you take an alcohol, we may demo this in lab, not this week, but not next week, but the next week. You take sodium and you put it in an alcohol, it'll start bubbling. Bubbles coming up. What are the bubbles? Hydrogen gas. Okay? So, it's a roundabout way, it's a redox reaction, it's a way to make your alkoxide from alcohols because sodium hydroxide doesn't work because alcohols are not acidic enough. So, we can do chemistry. Take this, treat it with sodium, make the alkoxide, right? Throw in a carbon, tetrahedrocarbon with a leaving group, and bam! SN2. Good nucleophile now, right? Make that bond. And what if we put on the oxygen? Another alkyl group. That is an sp3 carbon, so it's considered alkyl, although it has an aromatic further out. We just alkylated the alcohol. Alkylation of alcohols. What type of product did we form? Functional group here. Ether. So when you alkylate alcohols, you get an ether. This is called the Williamson ether synthesis. Making the alkoxide and then putting on the alkyl group by the SN2. Williamson ether synthesis. What about phenols? Now, phenols are more acidic than regular alcohols, back to pKa about 10. We can use hydroxide with phenols. This is a phenol. This is called the phenoxide. Phenoxide, P-H-E-N, phenoxide. Plus water. 10, water 16. Which side's favored? 16 is favored by how much? 10 to the 6. We have at least 2 or 3 log difference. This reaction will work in that. You can use hydroxide for phenols and carboxylic acids, just not for regular alcohols. So we can do a reaction like this. Then hydroxide, make the phenoxide, throw in something like methyl iodide. That's an iodide right there. Not an L. Iodide. All right. Very toxic. Why is methyl iodide so toxic? Bam. Because that's so easy. No steric hindrance. No steric hindrance on the carbon. Least amount possible. And iodide is an excellent leaving group. Methyl iodide is very toxic. It'll react with nucleophiles in your body, your DNA, proteins. Okay. So we methylated the oxygen. Methyl's an alkyl group. We alkylated the phenol. We made an ether. So this would be called a Williamson ether synthesis. Please be looking ahead. I want to say one thing on the previous page. Please be looking ahead, understanding this here. Then we need to be able to go backwards with our Williamson ether syntheses. Make this compound, give a synthesis of it. How would you make this ether? Just going backwards. So that synthesis there. We'll pick up there next time, guys. I have lab sheets for us.